So we're going to bake some cakes here. So how many cakes can you bake? So let me tell you what it takes to bake a cake. Well, to bake one cake, it takes 1 cup of milk. To bake 10 cakes, it's going to take 10 times that much. It's going to take 10 cups of milk. To bake a cake, it's going to take 2 cups of sugar. So to bake 10 cakes, 20 cups of sugar. To bake a cake, it's going to take 5 cups of flour. To bake 10 cakes, it's going to take 50 cups of flour. To bake a cake takes 3 sticks of butter. To bake 10 cakes is 30 sticks of butter. And finally, to bake a cake, it takes 6 eggs. So to bake 10 cakes, it's going to take 60 eggs. Alright, so now I want you to tell me how many cakes can you bake with the following quantities of each of these ingredients. So we're going to give you 10 cups of milk, 20 cups of sugar, 50 cups of flour, 30 sticks of butter, and 6 eggs. How many cakes can you bake with that list of ingredients on the right? Well, the first 4 ingredients, you have enough to bake 10 cakes. But the last ingredient, the eggs, you only have enough eggs to bake 1 cake. Therefore, you can only bake 1 cake. All the rest of those other ingredients you'll just have to put back on the shelf. You don't have enough eggs to bake more than 1 cake. In this case, eggs are what's called a limiting ingredient. Or in chemistry, we're going to call it a limiting reactant. It's the thing that runs out the first. So the third column can produce only 1 cake because there are only enough eggs for 1 cake. So limiting reactants deal with situations where one of the reactants is consumed, runs out before the other. In a limiting reactant problem, we want to be able to identify 1, the limiting reactant, the reactant that runs out first, and 2, the excess reactant, the reactant that is not completely consumed or used up. And 3, the amount of excess reactant remaining, as well as 4, the quantities of the products that can be produced. So in the following combustion reaction, 2 moles of O2 react with 1 mole of CH4. We've seen this equation quite a few times. But what if there are more or less than 2 moles of O2 for every 1 mole of CH4? Think about it. What are the chances that you're going to have exactly twice as much oxygen as CH4? That would make both of them run out at the same time if that's the case. If you have twice as much oxygen as CH4, whatever the number of moles is, if you have twice as many O2 as CH4, they'll both run out at the same time. But what are the chances that that happens? You're almost always going to have either more or less O2 than twice as much O2 than CH4. You might have 3 times as much O2 as CH4 or 1 times as much O2 as CH4. In either of those cases, one of the two is going to run out first. So we're going to learn how to deal with that situation. So then one of the reactants will run out before the other. The way to perform the excess reactant problem above is to run the reaction twice. So let's see how that works. Once in which all of the CH4 is completely used, and once in which all of the O2 is completely used. So here's an example. You're given 6.42 grams of CH4 and 34.2 grams of O2, and they're reacted in this combustion reaction with methane. Determine 1, the limiting reactant, 2, the excess reactant, 3, the amount of the excess reactant that's remaining, the number of moles of CO2 produced, and the number of moles of H2O produced. And we could take it one step further and have you calculate the grams of CO2 produced and the grams of H2O produced, but we won't do that here. We'll just stop at moles. So here's the amount of the reactants that you're given. So first, convert grams to moles. Remember, reactions only speak the language of moles. Reactions only speak the language of moles. You can't put grams into a chemical equation. So we need the molar mass conversion for CH4. There it is. So you need grams of CH4 to cancel out, which they do, and moles of CH4 to appear in the final answer. So 6.42 grams of CH4 is equal to 0.4 moles of CH4. For oxygen, we have 35.2 grams of O2. There's the molar mass conversion for O2. So what you have is 1.10 moles of O2. So those are the two numbers we're going to use in the chemical reaction. 0.4 moles CH4, 1.10 moles of O2. So here we go. We are now going to run two reactions. Reaction 1 uses up all 0.4 moles of CH4. Reaction 2 uses up all 1.10 moles of O2. That's the amounts that we have to work with. Set two rows of boxes below the reactants to run each reaction. So in the top row, that's going to be the reaction where we use all of the CH4. In the bottom row, that's going to be the reaction in which we use all of the O2. So now we're going to start filling in those four boxes. So that's what we're working with. Use all the CH4. Reaction 1 consumes all 0.4 moles of CH4. Reaction 2 consumes all 1.10 moles of O2 that we have to work with. So here we go. The box that's outlined in red, that's the CH4. So we're in the CH4 column, and that's where we're going to react all 0.40 moles of CH4. So we're going to put 0.40 in that box right there. Now we ask the question, how much O2 do we need to react all 0.4 moles of CH4? Well, the chemical equation shows us that relationship. We need twice as many moles of O2 as we have moles of CH4. Therefore, we're going to need 2 times 0.4 or 0.80 moles of O2. 2-to-1 relationship. Now we're going to go down to the lower level and we're going to run the reaction where we use all of the moles of O2. So below the O2, in the O2 column, down on the bottom level where it says use all O2, we're going to put the 1.10 moles right there. That's the reaction where we're going to use all the moles of O2. Now, how many moles of CH4 would it take to use all 1.10 moles of O2? Well, again, it's a 2-to-1 relationship between O2 and CH4, or stated another way, you need half as many moles of CH4 as you have moles of O2. So half of 1.10 is going to be 0.55. So if this seemed a little confusing, just remember all the relationships are 2-to-1. The chemical equation is 2 oxygen for every 1 CH4. The use all CH4 is a 2-to-1 relationship, 0.8 to 0.4. And the use all O2 is also a 2-to-1 relationship, 1.10 for O2, 0.55 for CH4. So the second column in all three cases is twice the first column. Okay, now we're going to see which of these reactions will have one of the reactants run out first. So what you're going to ask is, do we have at least this many moles to work with? At least, the phrase at least means that many or more. Do we have at least that many or more? So do we have at least 0.4 moles of CH4? And the answer is yes. We have exactly 0.40 moles. That's what we know that we started with. Now we're going to go over to the box on the right, 0.8. Do we have at least 0.8 moles of O2? And the answer is yes. We have 1.10 moles of O2, so we have more than 0.8 moles. So we have enough O2, in other words, more than enough to combust all of the CH4. It takes 0.8. We have 1.10 moles of O2, so yes, we have enough O2 to combust all of the CH4. Now we're going to go down to the bottom row, and we're going to start on the bottom right. 1.10. Do we have at least 1.10 moles of O2? Yes, we have exactly 1.10 moles of O2. That's what we started with. Now we're finally going to go back to the box on the bottom left. Do we have at least 0.55 moles of CH4? And the answer is no. We only have 0.4 moles of CH4. So what this means is that the CH4 is going to run out first. Okay, in other words, if we want to burn all of our CH4, we have enough oxygen to do that. We have more than enough. That's the top row. If we want to burn all of our oxygen, the 1.10, we don't have enough CH4 to do that. We would need 0.55 moles of CH4 to burn all of the O2. We don't have that. We only have 0.40 moles. So the CH4 is the reactant that's going to be used up first, and that's our limiting reactant. So we're going to put a box around this on the left. So the limiting reactant is the column with the no in it. So it's the CH4 column that has the no in it. And by the way, every time you do one of these problems, you're always going to end up with 3 yeses and a no. It'll always work out that way. The only way it wouldn't is if you had exactly twice as much oxygen as CH4. But in these types of problems, you won't have exactly twice as much. So CH4 is the limiting reactant. That means the other reactant, oxygen, O2, is the excess reactant, the one in blue. In other words, the reaction that we can run to completion to burn all the CH4 is the one that uses 0.8 moles of O2. And we have more than that. We have 1.10 moles of O2. So the excess reactant is the blue column with the 2 yeses in it. So now the question is, how much of the excess reactant do we have left over? And you can see the equation right down there on the bottom right. We had 1.10 moles to work with. We actually had to burn 0.8 moles to combust all of the CH4. So we had 0.3 moles of O2 left over. That's the excess. That's the amount of the excess. So we've answered 3 of the questions. What's the limiting reactant? What is the excess reactant? And how much of the excess reactant was left over once the limiting reactant was completely used up? Now, the row in the green box is the reaction that we can run completely. In other words, we can burn all of the CH4 with 0.8 moles, with 1.1 moles of O2. We have more than enough because we only need to use 0.8 moles. But we cannot burn all of the O2, the 1.10, with the 0.4 moles of CH4 we were given. So the reaction on the top, the one in the green box, the row with the 2 yeses in it, is the reaction that will actually run. The bottom row with the no in it is the one that will not run because we don't have enough CH4 to run to combust all of the oxygen. So this reaction will run because there are at least 0.4 moles of CH4 and at least 0.8 moles of O2. This reaction will not run because there is not 0.55 moles of CH4 to burn all of the O2. So we're going to run out of CH4 before we burn all of the O2. The row with the 2 yeses in it, the top one in it, is the reaction that will run. This is the reaction in the green box. Now we can compute the number of moles of CO2 and H2O that can be produced from the reaction. So what I want you to do is, you don't need to do any math here, you just have to observe. What are the relationships between CH4, O2, CO2, and H2O? So the equation tells us that we will produce the same number of moles of CO2, 1 mole, as moles of CH4. It's a 1-to-1 relationship. So if we were able to combust 0.4 moles of CH4, that means we'll produce 0.4 moles of CO2. Again, remember, think of those numbers in the chemical equation not as a specific number of moles, but as a relationship. So it's a one-to-one relationship. So in this case, we have 0.4 moles of CH4. We're going to produce 0.4 moles of CO2. We will produce the same number of moles of H2O, 2 moles, as moles of O2 because they both have a 2 in front of them. So if we consumed 0.8 moles of O2, we're going to produce 0.8 moles of H2O. And of course, you can relate, for example, the H2O to the CO2. It says we're going to have twice as many moles of H2O as we have of CO2, so it's 0.8 to 0.4. Just like on the left side, twice as many moles of O2 as CH4, so 0.8 to 0.4. So there's a lot of ways you can make those relationships. So using molar mass conversions, we can compute grams of CO2 and H2O if we wish, but we don't wish, okay? We're not going to take the 0.4 and the 0.8 over on the right and figure out how many grams of CO2. If you want to do that for fun, that's up to you, okay? Okay, now we're going to deal with a separate concept from limiting reactants. It can be related in some of the problems to it, but it's really a separate concept. It's called actual and theoretical yield. So the theoretical yield of products in a chemical reaction is the amount that the chemical reaction says that you should get. So when you do your stoichiometry equations and you come out with some number of moles or grams, that's the theoretical yield. That's what the equation says you should get. The actual yield is how much you actually get in the lab. So actual yield can differ from theoretical yield for several reasons. Among those, human error in measurement, or materials lost by remaining in the container, spillage, or evaporation. So some of your water, for example, if you're doing something with water, could evaporate, could boil away. And so you won't end up with as much as you thought you should. So the difference between actual and theoretical yield is measured by percent yield. And there's the formula. Percent yield equals actual yield divided by theoretical yield times 100%. Okay, so here's our problem. We'll compute the theoretical yield and percent yield for grams of water for the following balanced reaction if 6.5 grams of CH4 is combusted in excess oxygen. The actual yield in the lab was 12.09 grams of H2O. So what you actually measured in the lab in your cylinder was 12.09 grams. So let's see how that compares. Now, get used to this phrase. You'll hear it in the future. 6.5 grams of CH4 is combusted in excess oxygen. That phrase, in excess oxygen, means that oxygen is the excess reactant, meaning you're not going to run out of oxygen before you burn up your 6.5 grams of CH4. The CH4 will completely be burned up before you use up your oxygen. So that phrase, in excess oxygen, simply means oxygen is not going to be the limiting reactant. Okay, so this is a three-step problem. We're just going to do it kind of quickly. We have 6.5 grams. We have our molar mass for CH4, and that gives us 0.4 moles of CH4. Now we're going to move across from 1 mole of CH4 to 2 moles of H2O. So that means we have twice as many moles of H2O, 0.4 to 0.8. It's a 2-to-1 relationship. Now we're going to go back out through the molar mass of water, 18.02, and we're going to end up with some number of grams of water, and we'll show that on the next slide. So it was just a simple 3-step stoichiometry that we did very quickly. So there's our problem. Again, there's the reaction. So the yield of H2O from this reaction should be 14.4 grams of H2O, calculated below. And there's the stoichiometry of it, the 3-step equation to get us from 16.4 grams of CH4 to 14.4 grams of H2O. So that's what our chemical equation in theory on paper tells us we should end up with. But you can see from the question up above, the actual yield in the lab was only 12.09 grams of H2O. So the percent yield is computed as follows. Percent yield equals 12.09 grams of H2O over 14.4 grams of H2O. So the actual on top, the theoretical on bottom, you multiply by 100%, and that gives you 84%. So we obtained 84% as much water as our chemical equation said we should. And again, the difference is because of various real-world errors, human error, evaporation, things that cause it in the real world to not be the same as what we thought we should have gotten. So this means we actually obtained 88% as much water as the chemical equation predicted. All right, so that takes care of this lesson on limiting reactants and percent yield. And that's it. We'll see you on the next lesson.